Hi guys, welcome back. We're ready to get into some longer questions now. I know that a lot of you are worried about work energy, and I know we've done a number of problems on work energy, but here's the GDE, the Gauteng prelim question, question number 5. Seen a couple of you asking questions about it, but we're going to do this on air. We haven't got a caller, but if you'd like to talk to me about it, please give us a call. That number to dial 0861 058 262, and we'll get through it. So let's go and have a look at the question, see exactly what it says. Come on, grade 12s of 2011, we can do this. A wheelchair ramp. Now, when you read the question, make sure that you underline. It tells you what the length is, and it shows you on the diagram the length of 5,36 meters and a vertical height of 0,7 meters. Makes an angle of 7,5 degrees with the horizontal as shown. So I read from the question, put it on the diagram, and make sure that I've got it. Now, the next thing, it tells you a boy of mass 70 kilograms sits on his wheelchair of mass 35 kilograms. The wheelchair and the boy remain stationary at the top of the ramp. So in my answer book, what I'm going to do, and I can't draw wheelchairs very well, so I'm just going to draw something like that, and I'm putting a stick figure like that, and I'm going to say V equals 0 meters per second, and I'm going to say the mass now of the two of the boy is 70 kilograms, and the mass of the wheelchair, MW, is 35 kilograms. So the total mass, and I'm just doing this in my head as I'm thinking about the question, the total mass is going to be equal to 105 kilograms. Not sure if you can see that, but we'll just get it a little bit darker. Let's just select that right now and choose a darker color. There we are, and we've got it 105 kilograms. So we know that that's the case. The boy now allows the wheelchair to freewheel down the ramp. The frictional force between the wheels, so we've got a frictional force, and the surface of the ramp is 12,5 newtons. The rotational effects of the wheels can be ignored. What it says, the first part of the question, is calculate the mechanical energy of the boy and his wheelchair at the top of the ramp. Now, what's very important here is you've got to use the formula that you're given on your data sheet, and you've got to use it completely. Don't just think up a new formula. Use the correct formula. What do we know? We know that the mechanical energy, in any case, is equal to the potential energy plus the kinetic energy. Obviously, if you've learned to use EP and EK, you can do that. So that's the alternative. But I'm going to stick with the U and the K just so that we know it. Now, remember that U is equal to mgh plus the K is equal to half mv squared. We are now set to substitute in. And the important thing here is to recognize that the wheelchair and the boy sitting in the wheelchair, they're one thing. So we must add the masses together. My intuition about adding them together to get 105 was correct. We need to work with them as a system. They're working together. We want the mechanical energy of the boy and his wheelchair at the top of the ramp. So remember, he was stationary. Tells us the boy remains stationary. Stationary or at rest means the initial velocity is 0. We put it in on the diagram as well. So what we're going to do is we're going to substitute the values in, and let's see where we go. So the mass, 105, G, 9,8. The H value here was 0,7 meters plus half. The mass is still 105. The velocity here is 0 squared. Guys, I want to say this. for your benefit. And you need to listen to me carefully. Even though you know 0 times anything is 0, substitute your value into the formula. You must complete your substitution. If you just work out the mechanical energy equals the gravitational potential, you'll get no marks. You must show it's kinetic as well. So once we've substituted in, now we can start to do the calculation, and what we get is this value on the this value clearly equals 0. This value turns out to be 720.3 joules, and if we add 0 to it, that's going to be the complete answer. 720.3 joules of mechanical energy, but it is the potential energy, gravitational potential energy. Right, let's go to the next question. Having got that sorted out, we now are asked the following. 5.2, consider the boy and the wheelchair as one object. Draw a labeled free body diagram to show all the forces acting on the boy wheelchair system whilst freewheeling down the ramp. Now, guys, he's not stationary any longer. So, when we draw free body diagrams, please remember the important thing. You're going to represent the boy and his wheelchair as a dot, as a single dot. We then must make sure that we indicate all the forces acting on that dot. Now, the first force that we're going to show is the downward force, the force due to gravity, the force of the earth. I'm going to put it like that, and we're going to say it's mg. Now, there are two things that you need to be very careful of here, is that you need to make sure it's vertically downwards and that it's not just a line, that it is an arrow, because it's a force. And we're even going to say over here, we've put the label Fg equals mg, and we're going to tell people what this is. This is the force of the earth, the force due to gravity. You could say it's the weight, or it's the force of the earth on the system. It's the force of the earth. All of those labels are possible. Don't put them all in. I'm just giving you the alternatives. Okay, so what other force do we know that's acting while the boy in his wheelchair are moving down the slope? What other force were we told about? Well, if you look at the question, it's not difficult to pick up. Over here, we were told there's a frictional force. Frictional force acts in the opposite direction of motion. We know the boy in his wheelchair are moving downwards. So that tells me that frictional force must be moving in the opposite direction. It's up the slope. So if the boy was moving down the slope, then there's a frictional force. It's not a very big frictional force, but we're going to draw it up the slope. And we're going to say this is the force FF, which is FF is the frictional force. We could even put in the value, which is 12,5 newtons. It's not really required, but just for our own working, and we know that it's 12,5 up the slope. Just so that we've got that clear, this is the frictional force. There's something else that this object is being acted on by. Do you know of any other forces? Well, for sure, you're crying out and telling me, yes, there's another force. What is it? It's the force of the surface on the wheelchair. The wheelchair isn't hovering above the surface. It's touching the surface. So the surface pushes up on the wheelchair, and that's at 90 degrees to the frictional force. It is the normal force. I'm just going to erase this little bit here so I can put in the normal force. So we're going to say normal force, F normal, and this is the force, we call it the normal force. It's the force of the surface on the system, on the boy and the wheelchair system. Okay, so there are our three forces. That's one way of representing it in that diagram. Okay, there is another way of doing it where we look at the components of the weight. So instead of showing the weight, the force of the earth pulling down on the object as one vector, or as one force, we can say, guys, let's break it up into components. And I'd like to do that so that you've got that alternative. It does help us to sort out the system. But I do just want to make one little point here that helps us in our reasoning. If we extend this line over here, you need to recognize that we know this angle is 7,5 degrees. So just bear that in mind. You wouldn't represent that on the diagram. I just want you to acknowledge and understand where that comes from. That's 7,5 degrees, and we're going to be using that very shortly. So if we look at the components, what we need to recognize is that if we put the components together, that we'll get a second triangle. And that second triangle, I'm just going to draw on top of the first one to explain. You would not give this as your answer. You would say, well, look, there's a component that is vertically opposite to the normal force. It's the same magnitude. And then there's a component that is parallel. Now, this triangle shows the two components. So this is the component that is perpendicular, component of G perpendicular. This is the component parallel. So this angle here would be 7,5 degrees. The angle of inclination is equal to the angle between the normal, between the force of the earth and the perpendicular component. These two angles are equal, and this one is going down the slope. So if I have got that picture, now I think you can see that it's not terribly difficult to draw in an alternative free body diagram. Don't mix them up. Draw one or the other. So I'm going to start with the normal force, and I'm going to say, look, that's F normal. This one that is the same length as that one must be the same length. Opposite direction is V as F, the component of the gravitational force perpendicular to the surface. Then I've got the frictional force up the slope, and I've got this one which is bigger than the frictional force, because the force is the wheelchair is acting downwards, and it's going down like that. So if I label it like that, these are the components. I must now include a little key. This says normal force, which is the same as previously. FF, the frictional force, which we know the size of. And the next one, we're going to say F of G perpendicular. This is the component of Fg, of the weight, the force of the earth, or gravity, that is perpendicular at 90 degrees to the surface. And then the last one, we're going to say Fg parallel, and this is the component of Fg, which is equal to mg, that is parallel to the surface. Now, I really encourage you to make sure you understand these two diagrams, and that you make sure that you can break things into components, because sometimes you're required to use them. Let's move on to the next part of the question. It says, very important to read the question and to take note of where the hints are. Use the work-energy theorem to calculate the magnitude of the velocity of the boy and his wheelchair upon reaching the bottom of the ramp. Now, sometimes in the previous exam paper questions, they've actually asked you to state the work-energy theorem. You need to know the work-energy theorem. You need to know it really well. And what does it say? It says the net work is equal to the change in kinetic energy. And when we say change in kinetic energy, we mean final kinetic energy minus the initial kinetic energy. So that's the system that we're working with. That's what we're wanting to do. And what we need to recognize is that when we're looking at this, then we need to understand what the net work is. So what is the net work done in moving down the slope? We've just done the free body diagrams, and we'll be able to work that out. Remember, we define net work as the net force times the delta x times cos theta. And we're going to say that is equal to the final velocity, the final kinetic energy, which is velocity final squared, minus the initial velocity squared. Right, that's quite a mouthful. Let's go and break out exactly what we need to do. It looks to me like we're going to need to find what is the force that is actually causing this object to move down. And we go back to our free body diagram to determine that, and we're going to have a careful look at that. So if we look at the components, remember what we said in the terms of the components, that these two are equal. So the thing that is causing work to be done, the net work, is the difference between the force of friction and the force of G parallel. We could work it over here as well. We've got the force of friction, and notice here there's a different angle now. And if you recognize that this whole angle is 90, then this angle here is going to be 7,5 minus 90. So you could work it with that. You could say 90 degrees minus 7,5, and then you can work with Fg. But we know that it's these two forces added together. It's those components added together. That's another way of doing it. Let's see which way we're going to try it. We're going to take a look at seeing if we can get the different components together, and to make sure that we can sort it with that. So my first problem, let me actually go back to the diagram here, is my first problem is I know this F, I know FF is 12,5 and it's up the slope. I want to get this FG parallel. So FG parallel, if we look at our diagram over here, FG parallel, notice it's opposite. FG parallel is going to be FG sine theta. So I'm going to put that in, FG times sine theta. So that's the equation I'm going to use. Now, what is FG? Remember, it's mg sine theta, and m was 105, and g is 9,8, and sine theta here, don't get confused here, it's the angle of inclination. It's this little angle, it's that angle there. So we want 7,5. And if I do that, I'm going to just use the calculator quickly, just move it across so I can get the whole screen in. 105 times 9.8 times my sine of 7.5, and it gives me an answer of 134,31. 134,31. Let me write that down. 134,31 newtons down the slope. So what I've got 12,5 newtons up the slope. I've got 134,5 newtons down the slope. So the net force is going to be these two forces added together, the force parallel and the force of friction. But now I'm going to put my signs in. This is 134,31 plus minus 12,5, because it's in the opposite direction. So in my calculator, pull up the calculator, I'm going to have to subtract from this value 12,5, which gives me 121,81 121,81 newtons, and that's down the slope. And now it's really easy because I've got the resultant force, and I'm now going to use that over here. So it was 121,81 times, put it in brackets so that we don't get confused, times this distance, the distance that it's moving down the slope, 5,36. 5,36. Now what about the cos theta? This is the important point here. We've already done all the subtraction. We did force up, force down, resultant force. Resultant force is down. It's in one direction. They're in the same direction as the displacement. So it's going to be cos of 0 degrees. And we know that's 1. Now, let's substitute that in. And what we're going to see is the final velocity is what we want to find. So it's half times 105 times the velocity v final squared minus, and we substitute all these values in, 105 times 0 squared. Please substitute the 0 in, and you get your marks for doing that. And the end result is that you've got a, let's put this all together. This is going to be equal to minus, let's just use the calculator to do the calculation. We've got 120. Now let's multiply it by 5.36, and we get 652,91. 652,91. 652,91 is equal to, now I want to push the wrong button there. I want to do the other calculation. I'm now going to work out the this part of the equation. Half 105. So half of 105, which I really should be able to do in my head, but I'd rather trust the calculator. You can always trust a sharp. It's 52 and a half, 52,5. So 52,5 v final squared. Okay, so what are we going to do now? We're going to solve for v final squared is equal to 652,91 divided by 52,5. And if we do that, let's just clear this one. We're going to put it in 652,91 divided by 52,5 equals, I don't like that form, 12,436. If we round it off to 2 decimal places, that become 44. But we want to get the square root. Remember, don't forget the square root. So we're going to square root that answer, and we should get the correct answer in a minute. Let's go there. So we're going to say square root, and we're going to say we want the square root of the answer. Square root answer equals. And there we go. I've got the velocity here of 3,526. I'm going to round it off to 3,55. So the final velocity at the bottom of the 3,5, check it, 53. 3,53. 3,53 meters per second. Okay, well, that was quite a marathon to get that one out. Let's go to a short break. After this, we'll be back with another question.